It says the meeting is being live streamed now.
Yeah, I think it works now. Maybe I sent it to the wrong channel.
I see.
I mean, to a non-existent one. Yeah, I think it works.
Okay.
Okay, good. Okay, so we'll start in a couple of minutes.
Yep. Okay. You're still seeing my share screen, right?
Yes, yep.
Okay. I made the, oh, here we go. Okay.
Yeah, everything looks good. Mm-hmm.
Bars. Just keep one face here at the top.
Okay, I think we can get started. It's 2 p.m. here, so thank you for coming. So the speaker today is Professor Ezio Iacocca from the University of Colorado at Colorado Springs. He's been an assistant professor there since 2021. He received his master's degree in nanotechnology from the Royal Institute of Technology in Stockholm in 2010, and PhD in physics from the University of Gothenburg in Sweden in 2014, where he worked with Professor Johan Ackerman. Then he was a postdoc at CU Boulder and NIST under the International Postdoc Award from the Swedish Research Council, and then joined the Northumbria University in Newcastle, UK, in 2019 as a senior lecturer. He was there for 2 years, and then in 2021, he joined the University of Colorado at Colorado Springs as tenure track faculty in the Department of Physics and Energy Sciences. He is a recipient of the Department of Energy Early Career Award in 2023. So today he'll tell us about his work on explainable machine learning methods via the pseudospectral Landau-Lifshitz equation. So with this, I'll give it over to you, Ezio. Please take it away.
Thank you very much for the introduction, Kirill, and thank you, and thanks, Jim, for the invitation to give this seminar. Right, so this is basically, I'm going to talk about our work under this Early Career Award from the Department of Energy. Before I start, just a little bit about my group. So this is the current configuration of the group. Most of the work I will show today has been done by Cassandra Egan and Matt Koppus, who's my postdoc. And also we'll show some results from Alison Roxborough, who's now in Spoon River College. Kyle Rugwell also was a previous, well, he's still a member in the group, but he got a SCGSR award from DOE, so he's currently at Los Alamos. And this, if you haven't seen Colorado Springs, is a nice picture of our campus. You see the clock tower, that it's kind of the icon of the university, and in the background, Garden of the Gods, and of course, Pikes Peak. So if you haven't been in Colorado Springs, I encourage you to visit. Maybe not in winter, but well, depends what you like to do. If you want to ski, sure. If you want to hike, summer is really good. Okay, it's just pretty much the outline of my talk. I'll just give a brief introduction of machine learning and physics, and this comes from a non-expert in machine learning. So really we have started doing machine learning since this DOE award started, and we have been trudging our way through it and knowing what are the problems and how to fix them. So that will lead me to talk about what are the challenges in magnetism. So why magnetism can be problematic to use machine learning. And the solution we have found is to use this alternative representation for the Land-Lifshitz equation, which we call the pseudospectral Land-Lifshitz. And I'll show you two examples of how we have used it. And so one is the problem of Skyrmian annihilation, and the other one is well, not really a problem, but just representing magnetostatic waves. And with that, then I will transition to what we're doing right now. So this is a lot of what I'm going to show is really recent results. Some of them are not even finished. But what we're thinking about a statistical way to represent a pseudospectral model. And we think this will be useful towards learning. And in this case, the main well width. So we're doing a toy model first, but we plan to extend this to 2D and 3D to really predict any structure you will desire to have in your material. Okay, so let's start talking about machine learning. Basically, this is a cartoon I got from one of my students, and I think it really shows what maybe most of the physicists think about machine learning. I mean, I'll leave you to read it, but basically the point is that this person has this pile of stuff here. You put data, an answer comes out, and like it says, just steer the pile until the results start looking right. And, that goes pretty much against everything we know as physicists. We'd like to have a deterministic explanation. Even if you do something statistical, we want to have a good answer and know exactly how you get that answer. So, we're starting with the wrong foot, at least some of us, because we want this to be explainable or to know exactly what's happening in this black box. Now, of course, this is not only a problem of physicists. It's already a big, well, I wouldn't say a big field, but it's part of machine learning, which is explainability. And this is a figure from a really nice review article in NPJ Computational Materials, which is explained by machine learning in material science, particularly. It's very nice. I would encourage you to go through this paper. But basically in this figure, what they show is what you can do to explain what the machine learning or the deep neural network is doing. And there are two different trees here. Of course, I'm not going to talk about each of these examples. That's what the paper does. But basically, the upper tree here, which is explaining the deep neural networks, is what they call a post hoc analysis. So you first take your data, you train your deep neural network, and after the fact, you do something, one of these techniques, to figure out what the network learned. As an example that I think it's easy to picture is to say that you have several layers in your network, and then you feed each layer with some random noise, and you figure out what each layer produces. So that allows you to tell what kind of features each layer is learning. The other approach is to use explainable neural networks, and this is what they call anti-hoc. So you don't want to explain later, you want to create a neural network that by default allows you to understand what is happening. So these are kind of the two ideas here. Okay, so having said that, now what we want to do is material discovery. And basically this is a cartoonish way that I put into sort of think what is the process of this. So first you have a couple of materials, of course, not these rocks, but imagine some nice materials that you have. You're going to characterize these materials in several ways, say XRD, VSM, if they're magnetic, SEM, AFM, you name it. So now you have a bunch of properties associated with a material. So ideally, you're just going to put this in your neural network, and it's going to be like a genie that knows all the truth. And this genie is going to know exactly how the materials and properties are related. Now, knowing all this, ideally, the neural network can predict something new based on the knowledge from your previous materials. So then, I mean, continuing with the genie, of course, as a scientist, we're greedy and we want the best material possible for whatever we need. And the genie will then point to something, and because I like the Lord of the Rings, of course, the best material has to be mithril. So that's what we expect, right? The neural network has to produce a material, or in this case, material or some prediction that is informed by what was learned before. So things that exist. So basically, the thing is that this works because we have materials that exist and we have properties that we can characterize. So it's as good as that, is the data that you have. But sometimes you cannot probe all the possible materials and all the possible characteristics. So there is an interest in having this done numerically, because it's probably easier to do this. You don't have to grow the material or find the material or characterize it. You just put it in the code and get the properties that you need. So yeah, building database with numerical codes is becoming more and more important. And this is one example, which is called the materials project. They have many, many different properties that can be characterized. And as you can see in this plot, which can be found on their website, you can see that from 2011, the amount of information that they can produce is quite significant. All right, so that hopefully that gives you an idea of what's the angle I'm trying to take here, which is to predict materials based on existing information. So that means that when we go back to explainability, there's all of this. This is very good, but ultimately, and people in machine learning will tell you that as well, data is basically the most important part. Is your learning is only as good as the data. So that means that we need good models to create good data. So that brings me to magnetism. So of course, there has been some work on machine learning. This is not an exhaustive list. It's just some examples of what has been done. So for example, dynamics can be predicted. This is your standard problem. So basically, the idea is to learn the dynamics given the exact simulations. You can also put in the subtitle of Spintronics, but this is really nice work by Joey Chern. That I misspelled his name now that I noticed. But yeah, the idea here is to use machine learning to know or learn the many body problems. So now you can predict what the current is doing to your magnetic system. So in principle, is more efficient than trying to solve all the electronic system. And there's no space in the slide, but you can also predict other magnetic properties such as hysteresis loops and Curie temperatures and so on. So there has been work in magnetism, of course. Now, the angle we want to take is more on the creation of topological textures or maybe ultrafast dynamics. Those are two of the interests I have. So for that, you find another issue, which is the different regimes in which you can be in magnetic material. So this is a cartoon trying to explain that. So on the top, you have a piece of material with a bunch of atoms, and you can describe that with atomistic spin dynamics, right? So basically, you put your atoms where you want them, you know what are the discrete interactions between them, and you can model things very, very accurately. And this is good for far from equilibrium dynamics. It's probably the best model for ultrafast. However, it is quite time consuming because now you're doing atom by atom. And of course, you're also limited to small volumes just because there is so much memory you can use. So normally what people have done is the other regime of micromagnetics, where you basically take the spatial average of all this and condense it into one cell where you define a magnetization vector. So of course, that's very, very popular. Now you can have many more interactions, a much larger domain, the interactions become continuum. In principle, of course, it's still a PDE, so you will solve it discretely, but the idea is that now the equation is continuum. It's very good for equilibrium. This was done first to describe domains and domains walls. So it's really fast and large volumes. But of course, you cannot really access the far from equilibrium state very well. So that's all good. The problem is when you're in this, say, spatial average regime, right? When your features are big enough that can be challenging with atomistics, if you want to consider long range interactions, and too small for micromagnetics to really resolve it well. And when I say resolve it well, I don't mean that you cannot make your micromagnetic cells really small. What I mean is that the model itself is maybe not appropriate for that. So one example where this can be important is in the ultrafast motion of domains. So this is an article we published, I guess, almost 2 years ago now. Basically, this is a complicated problem to simulate because you have a domain pattern which exists because you have non-local dipole interactions. So you need the long-range effects. But when you come in with your pump and you excite ultrafast excitations, then all the dynamics really happen at the atomic level. So you have both of these worlds living at the same time, and it's really, really difficult to model. Even though we managed to do some model with micromagnetics after some simplifications. So what we found in this work is that there is strong evidence to suggest that domain walls can move really, really fast. So up to what we estimated was up to 60 or 66 kilometers per second. So very, very fast. Of course, it breaks Walker breakdown because this is basically a ballistic motion of domains. But, you know, we would like to represent this much better with a better model. So one part of the solution is multi-scale approaches. This, of course, also has been done. And once again, not an exhaustive list of what other people have done. But these are two examples that I think are quite clear to show. So one is this idea that you can have a finite element grid that smoothly connects to an atomistic grid, basically, which is atomic. Another really nice work was to do all this different ways of graining from the atomic to a continuum approach to have a really smooth transition. And this worked really well. If you check these papers, they will show how a skyrmion can go through this transition and discretization, and there's basically no reflection, nothing funny going on. The problem of this is that, of course, you need to know something of the sample. So again, if I'm thinking about ultrafast, where everything is ultrafast, I mean, everything needs an atomic degree of freedom, then it will suggest that you, again, need an atomistic grid at every time and every grid point. So presumably, we would like to have another type of approach that does not require structure to be grid independent. All right, so I'm almost there to tell you about the pseudospectral model, which is the model we believe is going to fix this. But to get there, let's just think a little bit about the dispersion relation. And I'll go back to the dispersion relation quite a lot in this talk because it's really sure, it's for small waves, but it tells you something about the interactions between cells and between atoms. So here I'm making an artificial distinction between the Magnum dispersion and the spin wave dispersion. Basically, what I want to say with this is that the Magnum dispersion is what we know. For example, this is a 1D chain, and you can get this directly from the quantum representation or discrete representation of exchange. And it has a cosine form, right? We have seen this before. And of course, if you take the long wave limit of this cosine, then this goes back to this k-square dispersion, which is also the sort of dispersion we're used for magnons or spin waves in a ferromagnet. Now, when you plot it, of course, you have a problem because as you approach the first Brillouin zone, then you have a quite significant discrepancy in the energy or the frequency. So that's, in my opinion, one of the reasons why it's so difficult to do ultrafast dynamics with micromagnetics is because you have this inflated energy when you have short scale interactions. So even if you keep discretizing your material finer and finer resolution, at some point, if you do it at the atomic level, you will end up with this immense energy. So it's not going to be physically accurate. So that's one side of the problem. The other side of the problem is the group velocity, and that might be a little bit worse, because if you take the derivative, then you have this tremendous problem that for the magnon, the real magnon dispersion, the shortest wavelengths have no group velocity, while in the micromagnetic limit, you have the maximum group velocity possible. So of course, there are some subtleties to this I'll come back to, but in principle, this is what the model is telling us. So our solution was to really take inspiration and work that has been done for fluid dynamics. So we need a new hope, and it's called well, we need to resolve the atomic scale. And this was not done really by Luke Skywalker, of course, it was done by Witham, and it's called dispersion engineering. So in spirit, it's a very simple idea. What Witham did was to acknowledge that it's really difficult to solve water waves, but it's kind of simple to solve KdVs, the Korteweg de Vries. So his idea was, can we modify Korteweg de Vries to mimic what Euler equations are doing? So basically, we took the same idea. In the case of fluid dynamics, they normally look at the phase velocity of the system, but we realized we can just look at some arbitrary kernel. So this is a pseudospectral non-Lifshitz model that we came up with. It's in its full glory here, but of course we have the same terms of your typical lambda Lifshitz. So first you have your conservative terms, and basically the main change here is that instead of having an effective field, we're separating the local fields, right? It's just that nothing special there, and the non-local fields. So the non-local fields, this f-1, this is supposed to be the inverse Fourier transform, and then you put some kernel here that is supposed to capture the physical interactions between the cells. So this, of course, is in Fourier space. So what that means is that what we're trying to do is a convolution in real space with just a multiplication in Fourier space. So that's it. That's all the idea. You just put a kernel that represents the interactions that you're interested in. And then, of course, you can add damping. I mean, in your typical way, alpha m cross, again, the H effect. So there are several benefits of doing this. One is that it's intrinsically grade independent because you're now putting everything in Fourier space. So it doesn't matter how you use your grid, your kernel, if it's defined well, it will have points associated with whatever grid you have. So it doesn't have any problems of reflections. It should always be defined correctly. It needs a Fourier transform, which could be bad, but it's actually not too bad because if you want to do a full simulation with non-local dipole, normally you do this in Fourier space anyway. So you kind of, depending on your boundaries, you can have the same Fourier transform used for both the dipole and the kernel, or not. So far we have applied it in 2D and 3D. One of my students, Varun Banga, is working on this. So we're close to have the boundaries ready. We think we have proved that this can be generalized to any magnetic order. So another of my students, Colin, is working on an antiferromagnetic representation, which was previously worked by Kyle Rockwell. So all of this, the initial idea of pseudospectral lambda Lifshitz, you can find it in this paper, but we also compare it with atomistic spin dynamics that were done by collaborator Thomas Osler, and we find really, really good agreement between both approaches. All right, so let me go back to dispersion. Let's see if this thing actually works. And this is, again, results you can find in this recent archive. So what I'm going to show you is several dispersion relations where we use two cells. One is an atomic cell, so we consider that this is the lattice constant of the crystal, and another is something much bigger, so 5 nanometers. So this is our approach where the kernel is now just a dispersion relation in 2D. And what I'm showing here is a cut through the middle of that dispersion relation. So we get what we expect. If you use a cell size that is the atomic lattice, then you get the full cosine. So basically you recover this equation. And if you use a much bigger cell, then you basically are zooming in here, so you only see the k-squared dispersion. So that's precisely what we expected. Now, because this works with a kernel, I can put whatever kernel I wish for. So we can do an exact micromagnetic model, right, where you only get a parabolic dispersion, no matter which discretization you have. Now, of course, you wouldn't like to use this because now this is going way high in the frequencies and energies. But the point is that these two are quite similar because that's is the regime where this approximation applies. Now, we also wanted to compare this to a micromagnetic model that is used. So we normally use MUMX3 in our research. So we thought, okay, let's use MUMX3. And we found something interesting. I mean, it's the kind of thing you notice after the fact and after you think about it. It's a micromagnetic model, but it does need a finite difference approach. So when you do the finite difference approach, the way it's implemented, you'll always, at least in this approximation, you will recover a cosine. So what it means is that if you compare all of these dispersion relations, you see that all of this agree. If you took the exact, say, Magnum dispersion relation in our approach, it is precisely what MUMX will tell you if you discretize MUMX at the atomic scale. Now, that's not supposed to happen. It happens because of how the finite difference was done. If you use different types of stencils, then this will change. It will still be a cosine, but the slope is going to be different. And you can see this now in the 5 nanometer cell, which is your micromagnetic cell, which this should handle better, and it's still a cosine shape. However, you don't need interactions that are up, down, and magnetizations that are neighboring each other in the cell. So you never get to that point in the first Brillouin zone, but my point here is that energetically you have a problem when you do all this type of discretizations. And in principle, when you use a pseudospectral approach, this will be resolved. Right. Okay, I'm going to show you now a few examples. So this is just the first simulation we did on ultrafast. We start with the same random initial condition. On the right, you see the difference. We're using the Magnum, the micromagnetic kernel. Of course, this is a mess. Every time you look at ultrafast dynamics, it's a total mess. But what we're interested in is to see what survives after this. How is the magnetization recovered? And the point of this simulation, although it's wobbly and things look chaotic, if you start noticing already now in the Magnum kernel, all the features are disappearing. While in the micromagnetic kernel, they're still around. And that's an important difference. That goes back to the energy, the additional energy that the micromagnetic kernel has. So if you were to use these models to compare with experiments, of course, if you try to compute the scattering out of each of these simulation approaches, you will get a different time evolution of the scattering. So this is one example where using the Magnum kernel on a pseudospectral model can be advantageous to explain experiments or to predict experiments. Okay, so I'll talk about these two examples. One is Skyrmion annihilation and the other is the magnetostatic waves. So for Skyrmion annihilation, we thought of this as a trial model or a example for the two-dimensional pseudospectral model. First, we had to add the DMI. Without going into details, it's really hard to represent this as one thing. So basically, I'm showing you is each field in each direction. The main point is that they're complex in Fourier space, and that's what gives rise to the non-reciprocity of DMI. We use material parameters as such that we found from platinum cobalt multilayers where different metals give roughly this sort of parameters. It's a relatively large DMI constant, relatively large anisotropies, it's out of plane, and also relatively high MS. Nevertheless, you can stabilize the Skyrmion like this. This comes from the ansatz of what the Skyrmion should look like, and then it's then relaxed with our model. So what we want to do is annihilate this. Again, and this is not supposed to be any inspiration for an experiment. What we're doing here is just take the initial condition and increase the field linearly. And we have to, just to make this viable, we increase the field at a tremendous rate. So if you see in the left movie, the field is going really, really high at nanosecond scales. But the point is that this is what you expect. The field is becoming high out of the plane. The Skyrmion is reduced and eventually explodes. Right? Nothing surprising. Now let's compare with the micromagnetic kernel. And again, this is real micromagnetic. You have a parabola. So as the field increases, you're making everything smaller, but now the energy is so high that the field cannot do it. So basically, you see this bouncing of the Skyrmion, and you need a much, much higher field to eventually annihilate the Skyrmion this way. So again, this is not supposed to be done experimentally at all because it's a very, very large rate. But the point is that with this model, you can hopefully have a much better understanding of how the skyrmions are stabilized and annihilated. So then, and this is all work by Matt Koppel, so he did all of the simulations to have phase diagrams of what happens with the skyrmions. So going relatively fast through this, the main thing here is that when you have color, it tells you which field it annihilates, and when you have this black, it's just direct annihilation. So this should be the right response, and this is after some bouncing. So once again, corresponding to the dispersion relation, the background kernel and MUMAX at the atomic cell agree almost exactly, whereas at 5 nanometer cell, our approach and the micromagnetic kernel also agree almost exactly. So again, I don't want to spend too much time on this. It's just a way to show that this kernel, as features become smaller, can better describe high energy interactions in a magnetic material. But what about the completely other range where you have really long interactions? We have a kernel, so we can use whatever kernel we want, as I mentioned before. So in this case, say, for example, you want to look at magnetostatic waves, and this is a nice figure, courtesy of my colleague, Dmitry Boschko. So you have surface waves that are going in this direction, backward waves and going in this direction. So when you look at the two-dimensional dispersion relation, it looks something like this, where you have two minima in the dispersion, and this is where you can condense magnons in a VEC. Okay, so we thought, can we use our model this way, which is definitely not for short interactions. So we went back to the paper by Kalinikos and Slavin from 1986. This is our picture of the general configuration, but we're now focusing only on the pi half, theta equal pi half. So everything is in plane, only surface and backward waves. So this is your dispersion relation, and you need to put several parameters here. So omega H, omega M, F, B. No need to go in excruciating detail here. The point is that with all these parameters, this omega DE represents the two-dimensional dispersion relation you saw in the previous slide. So solving this, what you find is that the kernel in the pseudospectral model looks like this, where here is where you find the two-dimensional dispersion relation. Right, so let's test this. And you can recover the surface and backward volume waves with this approximation. Again, this is fully two-dimensional, and we're just cutting the dispersion relation in two directions so you can see the surface and the backward volume wave. So this looks, at least qualitatively, what you expect. The surface wave goes up close to zero. The backward volume wave is backwards, so it has a negative group velocity in the beginning, and then it picks up when exchange begins to dominate. Now, is this good enough? We compared it with our normal Magnum kernel and the inclusion of non-local dipole interaction, and you can see that basically these dispersion relations are identical. So in principle, we're actually managing the interactions between cells relatively well. Oh, and I didn't mention, this is all done with a cell size of 20 nanometers, so you're way in the micromagnetic limit. This is the effect on thickness that obviously is a concern when you have magnetostatic waves. We excited at 11 gigahertz. And here you can see a comparison between several different approximations. The solid lines are backward volume waves. The dashed lines are surface waves. So black line is the dipole in 2D. So the the 2D simulations with dipole. Red is the dipole exchange kernel that we developed. So it's close when the thickness is small and then they diverge. And then we did simulations with BoomX3 in 3 dimensions. So when I say here 5 nanometer cells, I mean 5 nanometer in thickness. And in Indigo, it's much better resolved with 1 nanometer in thickness. So you can see that it's not too bad. It agrees relatively well. For the surface wave, you barely see any difference, except when you get to 50 nanometers. But of course, this is because I'm plotting primarily in the wave number. If you look at the wavelength, of course, it's inverse. And now the difference between all of these cases is about 15 nanometers. So it's a relatively okay approximation. And one of the reasons we want to do this, as we wrote in this preprint, is to possibly generate data much faster, so then you can train magnetic circuits or any magnet interaction done by machine learning with this method. Just two final examples before we move to the actual more neural networks is caustic beams. We thought we wanted to do something more than just exciting a wave. So what happens in caustic beam is that you choose frequency so as you have flat isocurves in your dispersion relation. So what happens is that the waves become narrow in one particular direction and typically are normal to the field. So you can see that, for example, and then if I turn the field, now the caustic wave is going, again, normal in the plane steel to that field. So it's a nice example to show that the approximation works. Okay, so in the last, I think, 15 to 20 minutes, I'll just talk about our statistical pseudospectral models. This is really where we're trying to get to discovery of new materials and using machine learnings. And the example we're working on right now is predicting domain wall widths. Okay, so this is the main idea. You have a crystal lattice. Everything is perfect. Everything is good in simulations. In reality, you probably have a defect, let's say a vacancy. So you don't have that atom. It distorts the lattice around. And then you have, variations in the exchange interaction. So what we wanted to, or our question was, okay, how can we model this? Because if you want to do this directly with micromagnetics or any numerical model, it's quite painful, right? Because you will have a hole in your magnetization. You need a large domain to have an average effect, and maybe you need to conduct several simulations and average them to figure out what is the net effect. So can we do something different? So as theoreticians, of course, is let's go back to 1D where things are easy and basically represent a chain like this. So each of these white spots is a vacancy. And then if you plot it as a function like this, right, when you have a material, you have, for example, 1, and when you have a vacancy, you have 0. So now this starts to look like random telegraph noise, right? It's basically discrete, and you either have signal or you don't have signal. And in this case, you can define sigma, which is the mean ideal material length, and then you have tau, which is the mean defect length. Right. So like I said, this is just random telegraph noise. Now that you have this, it's great because the random telegraph noise has been studied for years and years. So you just need to look up what is the Fourier representation. So what is the power spectral density of random telegraph noise? And this was done, for example, by MacLab in 1954. And you have a power spectral density like this, where this parameter T is just the sum of the inverses of sigma and tau. So you can define a defect density, which is basically 1 over sigma plus tau. So let's see how this looks like. Basically, if tau is equal to 0, you have no defects, and this equation will reduce to a single delta function. So its amplitude is going to be 1 here. As you increase tau, then this other term, which has the shape of a Lorentzian, becomes, well, it's first really broad. And as you can see, as you increase tau, it becomes bigger in magnitude and condensed, or the line width becomes narrower. So how do you implement this in a pseudospectral model? Well, we need a kernel that takes this into account. Initially, if you think about it, it's the magnetization multiplied by this random telegraph noise that will tell you where the defects are. So in Fourier space, what you're talking about then, it's a convolution between the magnetization vector and this Sk. So we're taking here the square root because it's a power spectral density, and it's already normalized, but we want it as a Fourier transform only. So now this thing in the parentheses represents what the magnetization with defects is. Again, in a statistical way, you should think about this because now everything is in Fourier. So if you do the inverse Fourier and you don't have a phase, it doesn't necessarily tell you, well, it will not tell you where the defects are. The idea is just to treat it as some average or mean values. And then the dispersion relation will just multiply this new defective magnetization. So we use parameters for iron platinum because we wanted a material with a really large anisotropy. So we're back to short wavelengths. So as you can see, this is about 7 mega amps per meter. So this will end up being something like 9 Tesla for a material that has a mass of roughly 1 Tesla. So on the left, you see the ideal dispersion relations. So tau is equal to 0. This is just to show that our implementation worked. And then when you have some finite tau, what ends up happening is that the dispersion relation is reduced. And this kind of makes sense, right? When, again, in 1D is maybe not as intuitive, but probably think about it in 2D. If you have a hole in your magnetization and you send a wave to that hole, that wave is going to scatter. So this is more or less what this is trying to say, even in 1D, that if you have a hole, there's less energy associated with that wave. So that's why the energy is reduced. So of course, this will have implications in domain walls, because now your exchange energy is reduced for small features. So in a material like this, where anisotropy is so large, then the anisotropy should become prevalent, and then the domain walls should become narrower, again, on average. Okay, so this is the logic of what we want to do. First, we want to simulate the dispersion relation. So there are two things you can do with this. You can either learn the dispersion relation, it's something we're working to improve, or you can go and simulate domain walls, as I mentioned. And after simulating these domain walls, you can calculate the width and then learn what the width is. So once you have all of this pipeline, then you can go the reverse way. I can say, what is the width that I want? And the neural network should tell you, okay, you'll get that width given this parameter sigma and tau. And finally, you can go back and figure out what your average domain wall would look like. So the point is, and the reason we think what we're doing is different, is that we're trying to predict statistical quantities that have physical units, right? Both the sigma and tau have, in this case, have units of nanometers or length in general. So the idea is that not to predict which material you need to use based on this crystal structure or this multi-layer, etc. What we're trying to say is, say you have a material that maybe you design from the dispersion relation, but then if you wish to have a structure, can you have that structure, or will that structure exist given this amount of defects, of this amount of defect density? So that's really the idea. It's not, again, it's not to say which material you need to use, but given a material you would like to use, how bad can that material be so you can have the texture or the behavior you expect from it. So for example, let me show you what we did to learn the dispersion relation. After several back and forth with different approaches, we realized that the convolutional neural network is the best approach because it's good for images. And basically that's what we can provide, is the two-dimensional dispersion relation, which is an image. So we use 32 nodes, 300 epochs, and a standard 80-20 train test split. So what I'm showing here is the test dispersion relation, so what we get from the model in red, minus the predicted one, so that way you can see it in two different colors. So that's at the very beginning of the epochs. So if we go on, this approximation gets a little bit better. So what you expect, or what you want, is to have this completely white. We don't get there yet, but as you can see, the approximation is much better. And we kept decreasing the epochs, but it doesn't really get better, so we're still working to see how to improve the convergence to a much better prediction of sigma and tau. But this is one of the things you can do. The other idea, or the other part of the project we're working on, is to do the inverse. Start from sigma and tau and have the neural network predict directly the dispersion relation we'd have without having to simulate it. Okay, but now let's talk about domain wall. So this is the ideal domain wall. As I mentioned before, we expect that a defective material will narrow it, and that's what we see, at least in this example. So then we can figure out what the widths are, and we do this with a simple definition that you can fit a line in the middle, figure out what the domain wall is when that line crosses 1 and -1. And then we can do this for a bunch of simulations, so this are the widths we get. Now, obviously, when you do things American, you can do whatever. Some things, or sometimes, might not be necessarily mean anything physically. For example, if you get to this point where tau is 100 and sigma is basically 0, well, this is the effective size of the domain wall in some particles that are sparse. I mean, that doesn't really have any physical meaning. But the point is that we can still create data. Maybe that's useful for for the learning. But if you think about it, physically, really half of this data is gone. This is really the regime you're interested at, which is where you have more material than defects. And in particular, you're really interested is in this little sliver here where you don't have many defects, which is expected from good materials, and see what the domain wall is. So this is really, really recent results. As you can see, the figures are not in a perfect resolution. But basically what we did for the domain, for the learning is to regenerate those domain wall widths, but now using randomly generated pairs of sigma and tau. So this is how the domain wall, as a function of sigma, what is the domain wall as a function of sigma? The color bar here is tau. And then this is another cut where you see it as a function of tau, and the color scale is sigma. So basically, once again, what we're probably mostly interested about is right here. The goal was to learn this and then predict it back from the width. So this should look more or less the same. The axes here are the other way around, but you would expect to have something like this. We don't see it very clearly. What we believe right now is because we have a multi-valued surface. So if you ask for width, there are many different pairs of sigma and tau that can give the same width. So we're working on ways to improve that, but basically still using a convolutional neural network, which so far it has been the most reliable for our purposes. So that brings us to the end of the talk. So that's where we are. The main thing we did was to introduce the pseudospectral model. It's grid independent. So the kernel is completely arbitrary, so you can use it to either define magnas for short interactions or magnetostatic waves if you're interested in long wave interactions, or you can put any other kernel to represent something else. But well, DMI could be inserted, some other interactions could be inserted as well. The other part of this talk was the statistical interpretation of the pseudospectral model, which was using this random telegraph noise and its spiral spectral density as a way to understand how, on average, the magnetization textures will behave. And the plan of this, these are all toy models and examples that we're building towards, but the idea is to really go to 2D and 3 dimensions so that you discover new materials. And basically the main message is that we want to predict what are these perturbations. And I would say the main question is, once you have a texture, say a skyrmion or a hopfion or any other texture, does this texture exist? Will this texture be robust to perturbations or to defects? And and if so, what is the maximum amount of defect you can have in your material? So those are the questions we're interested about. So with that, I'll conclude my talk. So thank you very much for your attention. I'm happy to answer any questions.
Thank you very much for this very interesting talk. Let's thank the speaker with the reaction buttons. So the talk is open for questions. If you have a question, please use the raise hand feature in Zoom, and I'll call on you. Alexei, please go ahead.
Hi, thank you for a very nice talk.
Thank you.
So I have a question. So we can have thermal effects, and there is a stochastic field that can describe those. Then there is colored noise that can be relevant at lower temperatures. So can this be simulated with this approach?
Yes. So that's a short answer. What we are now, because we're interested in ultrafast, we're putting temperature in. From a machine learning perspective, we haven't thought about it yet, like how to, I don't know if that was your angle, to how to implement it directly for learning. But in the model itself, yes, you can have thermal interactions. What we need to figure out is the right scaling for it, because obviously the thermal field scales with the volume of your cell. So when you use atomistics, well, the volume of your cell is as small as it can be. But as you increase that cell, then really what you're thinking is that the scaling represents a whole particle, it's not really grid independent. So that's something we need to work on to figure out how to make the thermal noise also grid independent.
Okay, thank you.
Yeah, you're welcome.
Okay, user Achintia, please go ahead.
Hi, I just had a very simple question about the sigma tau plot that you had.
Mhm.
When you said that you could discard parts of it due to it being unphysical.
Yeah.
Uh,
Mhm.
yeah, maybe I missed a part of it. I didn't understand that part.
Oh, what I meant is, so sigma tells you it's 1D, right? So sigma tells you the length of the material on average, and tau tells you the length or the size of the defect. So when you're under this diagonal, you're saying that you have more defect than material. So from that point of view, it's strange. The interpretation is strange because you have basically any material, right? In reality, a bunch of nanoparticles that are somehow interacting.
But you also said that it could still be useful as a
It
data.
could. What I meant is that sometimes, I mean, depends how it looks, but sometimes you want a more surface to achieve a better fitting. I think that's what I meant. So I guess what I was trying to do is a distinction between an approach where you can compute things that may not necessarily mean anything physical, and the other way of thinking is, well, I can have all of this data that maybe doesn't mean anything physical, but I can still use the data to learn my curve better. If
So I
that
guess
makes sense.
so I guess a judgment has to be made if it is
Correct.
useful enough without destroying the physicality of the system.
Correct. That's what I will say. Yes.
Thank you.
We're still not sure how important of this. So we still need to figure out how to better predict the width or the sigma and tau based on the width, and then we will compare whether we need all the data or we can constrain it to only the physical part of it.
Thank you.
I also have a question. So I want to ask about the point about the grid independence.
Yes.
So I understand what you mean if you have the kernel that is defined in the entire space of wave vectors, so that you don't have any cutoffs and you could potentially scale the grid down to infinitesimal. But in one of the examples you showed, when you use the Magnon dispersion relation, which lives on the lattice, so it's periodic in reciprocal space. It doesn't live in the whole space. So I'm not sure I understand how you can make this grid independent, because it already prescribes the Brillouin zone and therefore the lattice. How does that work?
You're right. So it's grid independent down to the lattice parameter. Yes. So that's the limitation. We impose that limitation as a physical limitation. So obviously it's going to be periodic. So if you keep reducing the cell size, what you're going to see is that this goes down again, and then you have two solutions. Yeah. Yeah.
But also, if your grid does not comply with the short wavelength part of that spectrum, that part is probably not faithfully reproduced by the simulation. Is that right? I mean, you can only reproduce the spectral features below the cutoff that is determined by your grid.
Yes.
That's correct, right?
Yes. Yeah, right. So if you increase your cell size, then you're, say, a little bit more, your first Brillouin zone will end here. Well, if you do twice as much, then you halve the Brillouin zone. And that's the best you can represent. Yes. So maybe, yeah, the point is when I say grid independent is, I mean grid independence as you increase from the lattice constant. So I mean, this is another idea that we would like to explore. Say you want to do back again to ultrafast, and you want to slowly change your discretization as the simulation evolves, so it can become more efficient. So really do a multi-grid expansion. We believe that this approach will give you a better way to do that multi-grid expansions without having reflection of waves as you increase the cell size. But this is a hypothesis, but we need to prove it.
Okay. Thank you.
You're welcome.
Are there other questions? maybe let me ask one more. So in that example that you showed when you vary tau and sigma, so in that case, the analytic solution for the domain wall width is not available, is it?
That's correct. So we have compared with the analytical solution. Go back there. The analytical solution when tau is equal to 0, which is basically this line, and we can get this to very good accuracy. But the rest is all computed in with this method. I mean, the detail is that we basically take a harmonic decomposition. So we take a cosine basis, duplicate this so it's even, and then you improve your approximation until you have a very good estimate of that line. So we can get this domain wall width to, well, basically the truncation accuracy, which right now is something like 0.1 nanometers. Of course, I mean, when you look at the width, this is a really, really small variation against a toy model to start with. But yeah, that's how we compute the domain wall width for any sigma and tau pair.
Okay. Okay. All right. So if there are no more questions, then we are going to stop streaming. And let's thank the speaker again.
Thank you very much.
And